So welcome everyone back from break. So we'll start. I'm going to start by a little bit of lecture and talking about just kind of where we are in the class before we get started with the peer feedback. So if you can find some seats, and then we'll maybe reorganize a bit later so you're in the discussion brackets. Yeah, so if you can find some seats now, and then we'll have a chance to regroup later. So everyone keep in mind, only one group can make it out of each discussion bracket, so get your pitch ready. I'm just kidding. So, yeah. If that was true, that would make it a little bit more interesting, right? So, okay, so, there's says I'm raising. Okay. Welcome back from break. Okay, what happened since last time we were here? There was a midterm. We graded the midterm. It was probably a little bit more challenging than I wanted it to be. So we readjusted how we did the points. I'm pretty happy, okay with where the scores so it turned out. The stuff on the streaming section, which we asked on the midterm, I'll probably ask about that again on the end term. Felt maybe that was probably premature to ask about based on how well you all did on some of those questions. But if you have kind of questions on the midterm or how it's graded, file a regrade request on Gradescope, and then we will look at it. Any big picture questions on the midterm, since we had that? Yep. I think if it's kind of a big picture thing, it's okay to email me. If it's about a specific question, a regrade request on Gradescope is easier to do. Yeah, I think at the beginning of the semester, I think the syllabus may have said to email me when we were still figuring out Gradescope, but just Gradescope is fine for regrade request. If you're worried about not being seen, you can always email to me. I read and reply to all my email. So it's a bad habit. So let's see. Has everyone signed up for the instructor feedback? Okay, so this week you are going to get instructor feedback from your project in addition to the peer feedback today in class. You need to sign up for that. Maybe you can send another announcement out on Canvas with just that link to the group feedback. I blocked a bunch of time in my schedule this week, and each group will get 10 minutes to come in, which I think if we do it efficiently, will be plenty of time for each of the groups. But I find this has been a really useful feedback for a lot of the groups around this stage in the project. I really want to emphasize the projects. I think they're a super important part of the class. Okay, and then the frequency estimation streaming homework is due on Wednesday. I hope it's not too challenging. You have to implement a couple of the algorithms, but they're hopefully pretty straightforward. good discussion on Canvas about it, and answer a couple how to interpret the outputs about them. Any questions on that? How many people have kind of feel like they've done or mostly done this already? Okay, all right. So and other people still need to get started, but it wasn't so bad, this one, or it was really tough. Oh, yeah, no, it was not so bad, or it was okay. All right. So hopefully this one wasn't so bad. I know there's a lot of stuff in the class this part of the semester. It'll cool off in assignments for the next month. Hopefully you're working on your projects. Okay, so we're starting a new section of class as well on dimensionality reduction. And so I want to kind of give an overview of this before we get into the peer feedback. I aim for this to be about 20 to 30 minutes. I want to kind of get this kind of started. Okay, so dimensionality reduction. And we're not going to talk about, I started out in the theoretical part of computer science. And this was kind of the first, we'll talk about random projections, which was the first technique I learned, but should not be the predominant technique you think of using. But I think it'll be a useful introduction, and we'll only spend like half of the lecture on it. But I wanted to introduce some main concepts, and we'll review them again on Wednesday. Okay, so we'll think of our data x. Okay, remember, we'll think of this as being x1 up to xn, and each data point will be in our D. So each of the elements, we're going to have n elements. They're going to be in D dimensions. Okay, and it's going to be implicitly that the distance between xi and xj is going to be the Euclidean distance between xi and xj. This is almost standard for the first 3 kind of lectures here, and then the 4th lecture we'll talk about if that's not the case. So we'll think about standard Euclidean distance. How I like to think about this is our data set is going to be as a matrix, where any of the rows of the matrix will be xi. Okay, so we're going to think of our data, and so that will mean that the number of rows is going to be n, and the number of columns is going to be d, the dimensions. N data points in d-dimensional space. And what we're interested in is when the d-dimensional space is very large. Okay, so when the dimension D is very large, and we want to map, the YouTube is working, or so map each of the xi, xj into our k, where k is much less than d. Okay, so I want to map it into a d-dimensional, into a k-dimensional space, a much lower dimensional space, where the distances still make sense. Okay, so now I want that the Euclidean distance between xj mapping and xi to be, say, approximately the original distance xi minus xj. Okay, so that I have some Euclidean embedding, or representation in the high dimensional space, but I want to go to a much lower dimensional space and then be able to still use Euclidean distance. Then I can do maybe nearest neighbor search more efficiently, or clustering, or I can just visualize the data because I'm in a much lower dimensional space. So this is the big premise of dimensionality reduction. Okay, so this is the big kind of picture of what we would like to do. What we're going to talk about today is kind of this random projection space. Okay, and this makes sense when, so this kind of makes sense if the original dimension is something like 100,000 or more, and the target dimension is maybe 500 or more. Okay, so this seems, these are big numbers. When I was learning about this, it was mathematical thing. Okay, their k is much less than d. 500 is way less than 100,000. But we didn't really have data that was this high dimensional, so it was kind of a theoretical thing to think about. And there's some really nice properties we can mathematical properties. And so when I first started teaching this course here, there was very little use for this approach in practice, actually. I've done research in this topic of dimensionality reduction, and this one's, okay, let's try and do this. When does this actually work? And it doesn't actually work that well unless you're really high dimensions to start with, and your target is still like 500 dimensions. Okay, in the last 5 or so years, this has changed a lot. This is now a really important concept, and kind of the when you can use it, when does this make sense to use, is becoming extremely relevant, especially in learned representations. So when I'm doing a learned representation of languages or of like images, there's kind of a native representation. Think of something like a one-hot encodings, or the kind of the bag of words, okay, or the kind of number of pixels in an image. That's giving us, you can represent these objects and they have like 100,000 or more dimensions in the representation of the input, okay? And we often represent them in 500, it started around 300, now it's often 1,000 or more dimensions of these sort of representations. And so this paradigm is not so unreasonable anymore, okay? It's painful to work with, so I probably won't ask you to do too much with this on your homework, other than maybe seeing that if you try to go to 100 or 50 dimensions, you kind of don't get very interesting results. Kind of like applying the general bounds you see in the streaming algorithm. You're getting off by 20% in the numbers I was giving you, because these are designed for much larger or settings. But in this paradigm, this is very important. Okay, before we talk about the technique, for dimensionality reduction in general, when can we apply dimensionality reduction in general? And this is another important point. I want to say that the distance xi, xj equals Euclidean distance xi, xj. This makes sense. Okay, well, what does this mean? We talked a lot about different distances, and kind of one, there are a couple of, there used to be kind of one kind of situation which was common, and that was when kind of all coordinates mean the same thing, or have the same, so at least they have the same like unit. Okay, so an example would be, I'm tracking prices of stocks. Okay, how do you track prices of stocks? You have a value, the stock price at the end of the day, say the value at time first day, the value at the second day, the value at the third day, up to the kth day, the k plus the k plus 1, the v k plus 2. And what you might do is say, well, I want to look at how this works over time, or I want to take the last k days and make a prediction on the k plus 1 thing. What's going to happen? Is the stock going to go up or is it going to go down? You might do some other conversions, like look at the, instead of not a 1 day, but the pair of days. There's some other things you can do, and you can kind of do a shingling on here where you can take k days and always predict the next day. And so then each of these block of k days, or maybe this should have been d days, gives you a d-dimensional representation of the stock price over the last d days. Each value is the price of a stock. Okay, so all the values are comparable in some way. I can do the same thing with looking at the temperature over a series of days. I want to predict what's going to happen on the next day. Or I have a whole bunch of weather stations, and there's this group on campus I've worked with that collects weather from over 40,000 weather stations around the US, and every station has like temperature, humidity, wind speed, stuff like that. They all have the same sort of coordinates on all these things. Okay, so all the coordinates are the same. But if you're mixing things like height and weight, you don't know how to tell the Euclidean distance between height and the weight because the units might change. Okay, so you don't want to mix units and apply dimensionality reduction. That's, if you mix units and apply this directly, you've kind of made some assumption in doing this. We'll talk about how to deal with this in kind of the fourth lecture in this section, if the units don't match. Then you'll have to do distance metric learning instead, which is a slightly different problem, but in the same kind of family of things. Okay, the second category, which is now becoming more prominent, is if you have a learned, or what's often called distributed embedding. Okay, so if we're doing kind of self-supervised learning to learn a high-dimensional representation, these often are trying to learn the cosine or the Euclidean distance, but embed things so the Euclidean or cosine distance makes sense, and the cosine distance is pretty related to Euclidean distance, so you can usually swap between them without too much too much effect. Okay, so if you're in one of these two settings where basically all the coordinates mean a variation on the same thing or the same units, or it's a learned representation, then the idea of how many dimensions do I need to represent this? Can I reduce them? Then this sort of question makes sense. Okay. If you don't have it, again, you don't want to apply these techniques if you're not in this sort of setting. You're going to kind of be, if you remember that sign I showed a picture from like New Koyama, where it listed the population, the data was found in the elevation, and added all those things up. That's what you're doing if you're mixing these units, because that's implicit in the Euclidean distance. Okay, so now we've got a data point, we have a data set, x2 up to xn, and these are all in a subset of Rd, and I want to project it down. I want to kind of find a projection mu of xj down to Rk. Okay, so how do I do a projection? Okay, there are some nonlinear approaches. We probably won't talk about those unless you ask me about them. Got opinions on them. Not talking about them because I think they're kind of wishy-washy. But we're going to talk about a linear approaches. When I do a linear projection, I'm kind of going from, you can kind of maybe draw a picture here. I've got some data points in some high-dimensional space. And what I want to do is find some low-dimensional subspace. And I want to project x onto this subspace here. We'll call this subspace F, right? And then this will be mu of xi, is the point that lives on this subspace here. How do I do this operationally? If you've taken the Foundation of Day Analysis course, you hopefully have seen this before, it's slightly familiar. We're going to start with the case we're going to start with where F is one-dimensional. Okay, and then I represent F is going to be a vector u in RD such that the norm of u is equal to 1. Okay, so this is a unit vector u. Okay, and then this map, which we'll call a projection onto the space u of x, is going to be defined as the dot product x u times u. Okay, so the dot product, what is the dot product doing? The dot product is, everyone don't remember what the dot product, how it works, Euclidean dot product? It's an operation that gives me a scalar. So if the direction u is along here, then what the dot product tells me is the length from the origin along this direction u. That's what the dot product tells me. It's the length. If I project x to the closest spot on that subspace, it's the length of that. But then it's only a scalar value. I want kind of a vector value. So then I multiply back by u, and I get a kind of a placement of that point projected onto that, well, subspace. Okay, so what space is this? So if I look at this object here, what is the representation of this object? Is it a scalar? Is it a vector? It's a vector. And what dimension is the vector? Well, the scalar, the dot product, the part I underlined in purple, gives me a scalar. U is a unit vector. What is the dimension of u? It's a d, right? So this gives me a d-dimensional vector again. Okay, so this gives me a d-dimensional vector. All right, so it lives in the same space as before. I started in RD, and when I do this operation, I get back in RD. If I wanted to just get into one dimension, right, this value, this gives me a one-dimensional representation. Just the dot product is just the length along that line. It can be negative if that is xi. If I have another xj down to here, this could give me a negative value because it's on the other side of the origin. So I can get one-dimensional value here, but the green part is in RD because the u vector is in RD. I'm just taking the unit vector, and the dot product tells me how much to scale it. It could be negative as well. Okay, so this is how I do a one-dimensional projection. Okay, if I want to do a subspace that's instead of one dimension, I will then say I can instead have f be k-dimensional. Okay, so then I need f to be defined by u1, u2 up to uk, and each uj is going to be in RD and as a unit vector. Okay, and I'm going to have that uj, let's say, is going to be orthogonal to uj prime. So this is an orthogonal basis. You can do dimensionality reduction if they're not exactly orthogonal, but typically you then want this. So then the projection onto f of x, I'd somehow need to combine together x uj times uj. So how do I combine together j of these? I'm just going to take the sum. Okay, why does taking the sum of these vectors make sense? Well, if I think of, I'm in a high dimensional space and I have, draw it like this. So if I have u1 and U2, and I'm living, I have a point, it's a high dimensional point, I'm projecting it onto the basis of these two things. I get a component along U1, component along U2, and I can do vector addition to get the projection onto F. Okay, so I get a component on these orthogonal pieces, and I can add up the vectors. I'm adding up d-dimensional vectors. I'm still in a d-dimensional space. Okay, I can also, okay, but I wanted to go to a k-dimensional space. This is a d-dimensional space. How do I get to a k-dimensional space? Okay, to get to a k-dimensional space from so if, again, this is U1, U2 up to UK, and I want to project F. Now I want to RK, I need to keep those coordinates individually. So now I can define X is going to be equal to a vector now, a k-dimensional vector, where the first one is X U1, the second coordinate is X U2, third coordinate, and so on, up to the kth coordinate is X UK. And now I'm into this. So now I've got a point that I've projected. This is now a projection of X here. And now it's got two coordinates. This is the coordinate X U1, and this is the coordinate X U2. And it's a two-dimensional space. I don't keep track of coordinates that are coming outside the projected onto plane. I'm only keeping track of coordinates in the new subspace. Okay, this is the kind of the mechanism of how projection works. We will review this again on Wednesday. It's a little bit, I think it's good to see this twice, maybe 3 or 4 times to kind of let it kind of sink in. Okay. Okay, I finally, before we go into groups, I want to talk about how do we find, so how do we choose this set F, this, which is defining this subspace, that's defining these unit vectors to project to do dimensionality reduction into a good space so that the distances make sense. Okay, any thoughts on how do we choose this space F to project onto? Okay, SVD, great eigen, which is related to eigen decomposition. We'll talk about this on Wednesday. This should be kind of the first tool in your toolbox for this sort of approach. But today we're going to talk about a different approach, which again has these limitations on when you can use it, but is called random kind of choice. And we're talking about random projection dimensionality reduction. So I'm going to choose UI random from the space of unit vectors in D dimensions, right? The points on a sphere. Okay, so the random projection. So I'm gonna for j equals 1 to k, I'm going to choose uj from randomly from the unit vectors in d dimensions. Do you remember how I choose a d-dimensional unit vector? Talked about this a little bit earlier in the semester. How do you actually have to do this on a homework assignment, right? How do you choose a d-dimensional random unit vector? Is that a hand? The Box-Mueller transform, that's right. So I can do this by selecting G1, G2 from normal, right? And then I do UJ1, UJ2 from the Box-Mueller G1, G2, and I do this, so I do UJ1, UJ2, and I repeat this up to UJK, and I get, or D, I need D of these. I get D, basically normal random variables, and I transform them. I can do uniform. This can be uniform 0, 1. I transform them. They become kind of these are uniform. I transform them into Gaussians, and then I normalize. I can put them into a d-dimensional Gaussian, and then I normalize it so its length is 1. Okay, this would be a uniform, so random dimension. This gives me one of these values. Okay, then I say that the Q of I is kind of J. This is going to be the J kind of coordinate of projection of my input pi x. Okay, so this J coordinate is going to be uj dot x, right? So I'm just taking this dot product. I get qij. I get a vector qi is going to be qi1, qi2 up to qik. I do this 8 times inside the for loop. Okay, and so yeah, so if I do this k times, this is almost my representation. The problem is this will tend to be too small. So turns out I want to multiply it by d square root of d over k. Okay, I need to inflate it a little bit because when I take a high dimensional thing and I project it, the length can only get smaller. Okay, and so you have this nice property. I'll just say 2 more things and then we'll wrap up for today. The expected squared norm of ujx is going to be 1 over d times the squared norm of x before the projection. So this is one coordinate, the squared norm, because I'm basically picking a random direction out of the d different directions, and I can, by Pythagorean theorem, I can decompose it into the squared norm into the sum of the d components, each square. And I'm picking one of them at random, so the expected length, squared length of this is 1 over d times original length. But I have k of these things I'm adding up. So I get the expected squared norm of qi before this normalization is going to be kind of k times, or is going to be 1 over d is going to be k over d. And I want the regular norm, so I need to multiply it by the square root of d over k to get the expected right length here. Okay. So I need to inflate it a little bit here, so I have to inflate it a bit. Okay, one other point is that how big should I make k? Okay, so I want to have the property. So I will want I'm going to write the answer here, and then I'll explain it on the next slide. Okay, we're going to have it where I have n data points. So I will want the property that xi minus xj 1 minus epsilon is going to be less than or equal to projection of xi minus projection of xj 1 plus epsilon x minus xj. So I want that the distance, my original Euclidean distance between the points after the projection, is within a 1 plus epsilon factor. Think of epsilon as like 0.1, so it's like 10% error. on all the distances. I want this to be true with probability 1 minus delta for all n points. Then I need the projection to go from RD to RK with K equals roughly, and there's like a constant like 1 or 2 in front here, but 1 over epsilon squared times log of n over delta. Okay, so if I want it to be 10% error, I need like a factor 100. And if I need, but I need it to be logarithmically depending on the number of points I need to preserve. Okay, so if I want n different data points to be roughly preserved, I need roughly only log n dimensions. I mean, I can cram a lot of information down into a much smaller dimension with the blow up based on how much space I want to preserve. And so this blow up of about at least 100 to get 10% error is why I say you really need to go down to about 500 dimensions to really trust this. If you go down below that, I start to get I'm allowed to have a lot of error on the projection. But if I'm in a 500 or 1,000 dimensions, I can fit a lot of stuff in there. And random projection is basically the best you can do. There's some deterministic things where you can maybe get rid of the dependence on delta if you're really careful, but they're super complicated. So everyone, for this, when you're going from like 100,000 down to 500, random dimension works about as best possible and is really easy to do. Okay, it's pretty straightforward to run the algorithm. You pick a bunch of these unit vectors using your random, you create the random Gaussian things through the Box-Mueller, and then you normalize them, you get these unit vectors, and then you just project onto k unit vectors, and they're not exactly orthogonal, but on average they're pretty close to orthogonal, and you still get the same. It works even without kind of forcing them to be orthogonal. Okay, so this are really kind of simple to use, powerful techniques. This is a very strong guarantee. So I preserve the distances, and that means all the algorithms I run with the distance I can now do instead of 100,000 dimensions in 500 dimensions, which not a lot better, but it still could be exponential indeed. That will still be a problem. But reading the data takes a lot less time with 500 dimensions than 100,000 dimensions. So this, and representing it with these vector databases, they all kind of use this under the hood in some way, either explicitly in some cases or implicitly. Okay, so we'll talk more about this and from a PCA perspective starting on Wednesday. Any kind of questions on this random projection stuff? Happy to revisit a little bit Wednesday if you want to. Cool. Okay, cool. So we'll stop the lecture here and we're going to break into the kind of, let me show the groups again. So I don't know if you can read these, but okay, what we're going to do for groups, you're going to break into a bracket for each of your groups. They're around the room, and there are a bunch. You can use the hallway as well. And I want you to exchange reports with each other, with your group. Spend about 5 or 10 minutes reading the other group's reports, and then take turns giving each group feedback. We've got about 45 minutes. So think about 10 minutes to kind of find your groups and read things, 10 to 15, and then about 10 minutes each to give feedback to each of the groups. And so myself and so Elham will be going around and checking out stuff. Okay. And you are being graded on this discussion right now. So
from today, or the first one today and the second, the two other from the.
So I mean, like this, the intermediate report is basically they turn something in, right? And we'll check that, and then I'll see it over the week, and then the group. They get these points when they come in and they discuss with me, and they get the first points today. So we want to go and check to make sure all the groups are participating in some way.
So this second and third will happen during the week, right?
Well, the intermediate report should be turned in today at noon.
I see. Okay.
Right, so that
Yeah.
Hopefully they can refine it. That's just for their own purposes.
Okay.